So the strategy for dealing with a dependent source like this one is to write down the equations that describe what's the voltage or the current that is generated by the dependent source and substitute it in. So basically it gives us kind of another set of equations or another equation that we need to include in our system that we're analyzing. So I'm going to look at this circuit here. We're going to solve for current I1 in this particular circuit. So to do this, I need to label my meshes. So I'm going to label this mesh current here as I1. I'm going to use the same name I1 as I1 here because they are actually the same current, but I'm just going to draw it with the circular arrow so it's kind of super clear that I'm talking about a mesh current there. I will also have I2 and I3 as my other meshes. So let's have a look at what's going on with that dependent voltage source. So in particular here, I can analyze the voltage V0, and I can do that using Ohm's law. And so if I analyze that by Ohm's law, then what I will get is that there's a combination of mesh currents. So I use Ohm's law to be positive for currents that flow from positive to negative. So if I look at I3 and I look at the direction of I3, I3 goes positive to negative. So here I have a positive sign for I3, whereas the I1 mesh current goes the other way around. So I should use a minus sign for I1 there. However, the voltage source actually specifies minus 3 V0, and so just for some convenience, I'm going to go and calculate what is minus 3 V0. So substituting in here is going to give me minus 9, I3 take I1. All right, so now we're in a position to go ahead and use our mesh analysis. So if I write Kirchhoff's voltage law at the first mesh, then here is what I will get. So I'll choose a starting point, let's say here, and we'll proceed around our circuit. So firstly, I encounter a negative of a supply, and the voltage there is a negative 3 V0. So to pay attention to these negative signs, because I'm starting on, or I'm approaching the voltage source from the negative side, that gives me a negative. And then because of the voltage has a negative sign, I get an extra negative sign there. The next component I encounter will be the 14 ohm resistor, and there'll be a current I1 through that to generate my voltage. The next component will be the 3 ohm resistor, and that one has a contribution due to I1 and also contribution due to I3. And then finally the 2 ohm resistor, which has a contribution due to I1 and a contribution due to I2, and all of that is equal to 0. So we can simplify, and we can substitute what we know about V0, because I've just calculated 3 V0 above. So I'm going to substitute that in, and I'm also going to clean up this equation a little bit. So negative 3 V0 is negative 9 I3 take I1. Looking at the other terms, we can start to simplify. So all of the terms involving I1 are going to give me 14 plus 5 is 19 I1. The terms involving I2, there's only one of them, so it's a minus 2 I2, and then I3, I only see one, so that's a minus 3 I3, and there's no constants, it's just equal to 0. That first term can be tidied up a little bit, so the negatives will cancel, and I'll be left with just 9 I3 take I1, and I'll just copy the rest of my equation. Minus 2 I2 minus 3 I3 is equal to 0. Then we can look at the terms involving I1. So there's a plus 19 and a minus 9, so that's going to give me 10 I1. The terms involving I2 stay the same, and then for I3 I get a plus 9 and a minus 3, which gives me plus 6. I3 is equal to 0. So that will be equation number 1. Next step will be to apply KVL at mesh number 2 at the second mesh. So again, we choose a starting point for our analysis. So let's go here and proceed in the same direction as I2 is drawn. So that's clockwise. So I'll go negative 25 for the voltage source. The 2 ohm resistor has I2 minus I1 as its currents. There's a 5 ohm resistor which has I2 minus I3. Then voltage source plus 10, and I'm back to my starting point equals 0. So we can simplify this equation a little bit. So the terms involving I1 is minus 2. The terms involving I2 will be 5 and 2 is 7, 7 I2, and then I3 is minus 5. Then there's negative 25 plus 10 is negative 15, and I'll bring it to the other side and becomes plus 15. So that is equation number 2. And then my last circuit analysis step, KVL at mesh number 3. So let's choose somewhere to start. Let's go here. And so we will have negative 10 volts plus Ohm's law across the 5 ohm resistor. So that's going to give me I3, but the opposite direction one is I2. Then I have 3 times I3 minus I1 plus just 1 times I3 and equals, that was all done, so equal to 0. Simplifying this one, terms involving I1 is just the minus 3 there. The terms involving I2 will be minus 5 I2. And then I3 will give me, there's a 5 plus 3 gives me 8, plus 1 is 9. 9 times I3, and the 10 comes to the other side to be positive. So plus 10, and that will be equation number 3. So in this particular case, I'm trying to solve for just one of my currents. And so because I'm solving for just one, a good method here would be to use Kramer's method. That lets me write down a mathematical expression for just one of the variables in my 3x3 system. So in order to do that, I need to express this as a matrix. So I will have a 3x3 system, and I will read off the coefficients. So I have 10 times I1, a minus 2, and a 6. So this is from equation number 1. That one is multiplied against these variables, so they are I1, I2, I3, and the right-hand side was just a 0 there, so that's equation 1. Equation 2, minus 2, 7, minus 5, and 15. And then finally reading off from equation 3 will give me these numbers. So to use Kramer's method, here's what I need. I need to calculate matrix determinants of two matrices. So I need to know the determinant of this A matrix. So the determinant of that matrix will be as follows. So I'm just going to pretty much write these down. If you're not familiar with this pattern of how to evaluate determinants, then go back and have a look at the video that I made about solving simultaneous equations using Kramer's method, and it will show you in a little more detail the pattern for how to actually go and do this. For these 2x2 determinants, I will analyze those basically just typing it straight into my calculator. So this one is 10 times, and then I'll just multiply this out. So this is 7 times 9 minus the product of the two negative 25s will just, two 5s will be 25, so that one is 38. Then I will have plus 2 times, let's type this one out, so it's negative 2 times 9 minus 3 5s is 15. So that is negative 33. And then last one here will be 6 times negative 2 times negative 5 minus 7 times minus 3 is 31. You've got to keep your wits about you with all the negative signs when doing this. But let's just go ahead and calculate that one. So that's 10 times 38 plus 2 times negative 33 plus 6 times 31 is 500. It's a very nice round number. So this comes from the textbook, so they've obviously chosen numbers that give sort of nice round answers. The next thing that I need for Kramer's method is the determinant of matrix N1. I want N1 because I want the first variable. And so to form this matrix, what I do is take the right-hand side over here and substitute that with the first column. So first column because I want first variable. So that's 0, 15, and 10. And then I read off the other columns from the original matrix. So the other columns were -2, 7, and -5, and then 6, -5, and 9 respectively. So to evaluate this determinant, well, that's 0 times, well, this block. Don't really need to bother with that one because it's multiplied by 0. There'll be a minus of -2 times this determinant. I will just write it out. Finally, plus 6 times this determinant. First term, well, that's just 0, so nothing particularly needed there, just because it's multiplied by 0 at the front. Second term will give me, the negatives will cancel, I'll get 2 times, and I'll just multiply this determinant out, so that is 15 times 9 minus 10 times -5 is 185 plus 6 by, again, bear with me, 15 times -5 minus 7 times 10, so that one is -145. Then 2 by 185 minus 6 times 145 is -500. So therefore my first unknown, which was I1, is determinant of N1 divided by determinant of A. So determinant of N1 was -500, and determinant of A was just 500. So this is -1 amps. So in this way I can sort of go straight to the answer for one of my solutions. So just to summarize, like, the key takeaways from this example is that when you have a dependent source like this one, the strategy to approach it is to write down the equation for the constraints which apply to that source and write them down in terms of your mesh currents. And if you write them in terms of your mesh currents, then you're able to just substitute them straight in to the equations that you generate when you do KVL. And so in that way, you substitute it in and just let the algebra take care of the rest. So that's basically how we analyze circuits that have dependent sources in them.